Welcome to the deep dive. Today, we're plunging into some really fascinating research. It's right at the intersection of AI, specifically how we get models to understand and generate discrete data. Think text, basically.
Yeah, we've got this paper here, the diffusion duality, and it's definitely stirring things up with some new ideas about diffusion models for language.
So think of this as your shortcut, your guide through the dense stuff. We're going to pull out the key insights from this paper for you. We'll hit the main concepts and, like you asked, really zoom in on what's genuinely new here. What's the mission today?
Okay, the mission is, first, to really grasp this core discovery they're calling the diffusion duality. Understand what that is. And then see how the framework they built on it, it's called Duo, uses that discovery to make a certain type of discrete diffusion model much better.
Which type was that again?
Uniform State Diffusion Models, or USDMs. The goal was to make them more competitive, especially against other models, and crucially, way faster at generating text. So theory into practice. Okay, got it. Let's set the scene a bit. We hear diffusion models a lot, usually for those amazing images, right? Stable diffusion, things like that.
Right, and those generally work with continuous data pixel values, colors, things that exist on a spectrum.
But this paper tackles discrete data. Words in a sentence, code tokens, distinct units, not a smooth range.
Exactly. And discrete diffusion models, they work differently. They usually take clean data, like a sentence, and mess it up gradually. Maybe swap words for a mask token or random words. That's the forward corruption part.
Adding noise, but discrete noise.
Precisely. And then the model's job is to learn how to reverse that mess, step by step, starting from total noise and hopefully getting back a coherent sentence.
Okay, and then there's the other kind, Gaussian diffusion, which is continuous. People sometimes try using that for text by working with word embeddings, those continuous vector things.
Yeah, that's been tried. You take the discrete words, turn them into continuous vectors, add Gaussian noise, learn to denoise the vectors, and then somehow turn them back into words.
How well does that work? Well, the paper points out, and it's generally known, that while Gaussian diffusion is super elegant for things like images, applying it directly to embeddings for text, it just hasn't really performed as well as models built specifically for discrete data. Something gets lost.
So you kind of had these separate worlds, and within the discrete world, you had different models too. You mentioned USDMs. What were the others?
The main comparison point is often masked discrete diffusion models, or MDMs. And prior work had actually shown MDMs tended to perform better than USDMs, like on standard metrics.
Right, even though USDMs had that interesting self-correction thing.
Exactly. That's a key property. USDMs, during generation, can actually go back and revise tokens they predicted earlier as more context becomes clear. It's like editing your draft as you write.
Whereas MDMs are more final.
Generally, yeah. They tend to mask tokens, then predict the unmasked ones, and once a token is predicted, it's often fixed. Less room for later refinement during that single generation pass.
Okay, so USDMs had self-correction, but maybe worse metrics historically. MDMs had better metrics, but less self-correction. But both had a big problem compared to, say, standard large language models.
Speed. Yeah, a huge speed problem, particularly generation speed or sampling.
Right. Diffusion models need all those steps to go from noise back to data. Hundreds, thousands.
Sometimes, yeah. Which makes generating text incredibly slow compared to an autoregressive model that just spits out one token after another.
And you mentioned MDMs couldn't easily use some speed-up tricks that worked for continuous models.
Right. Specifically techniques like consistency distillation. These rely on something called a probability flow, ODE, basically. A smooth, deterministic path from noise to data. Continuous Gaussian models have this.
But discrete models like MDMs don't.
Generally, no. Their discrete nature, the masking,
Yeah.
it doesn't naturally give rise to that kind of smooth, deterministic flow in the same way. So you couldn't directly apply those powerful distillation methods to speed them up drastically.
Okay, so the landscape was discrete models were slow. MDMs beat USDMs but couldn't use the best speedups. Gaussian models didn't work well on text embeddings. Seems like a bit of a mess.
It was definitely challenging, and this is where the paper drops its bombshell, the diffusion duality.
Okay, the core idea.
Yeah, the really fundamental insight. They discovered and proved mathematically that USDMs, those self-correcting ones, naturally emerged from underlying continuous Gaussian diffusion processes.
Whoa, hold on. So the discrete USDM process is somehow built on top of a hidden continuous Gaussian process.
That's exactly it. It's like finding out they're two sides of the same coin. Or maybe the USDM is a specific way of viewing or discretizing an underlying continuous process. They show formally how the probabilities of the discrete tokens in the USDM relate, often through an argmax operation, to the state of this hidden Gaussian process.
So it's not just an analogy, it's a direct mathematical link.
A rigorous link. And this connection, this duality, is what unlocks everything else. It suddenly means that all the powerful tools and insights developed for continuous Gaussian diffusion might now be transferable to discrete USDMs.
Because they're secretly related.
Exactly. It expands the design space for USDMs massively.
Okay, that's a really cool theoretical leap. So let's get practical. What's the first big win they get from knowing this duality exists?
First win. Training speed and stability. Because they understand this underlying continuous process, they can use it to guide how they train the discrete USDM. They introduce a curriculum learning strategy.
Curriculum learning, like starting with easier examples.
Sort of, yeah. The continuous view provides a natural notion of easier. They can start training the model on tasks that correspond to denoising slightly noisy data early in the continuous process and gradually ramp up the difficulty to highly noisy data.
And how does that help?
The paper shows this significantly reduces the variance during training. Less variance means the training is more stable, converges faster.
Then the result.
They literally double the training speed of USDMs. Cut the training time in half. That's a huge practical benefit.
Wow. Okay, faster training is great. Does the quality suffer?
Actually, it gets better. Models trained with this Gaussian-guided curriculum not only train twice as fast, but they also achieve state-of-the-art results among diffusion language models. They even beat standard autoregressive models on perplexity on, I think, 3 out of 7 benchmarks they tested.
So USDMs trained this new way are suddenly competitive with the big guys.
On some key metrics, yes. And they show better likelihood scores too, which ties back to that lower variance and better model fit. So win #1. Faster training, better performance.
Okay, huge. But what about the elephant in the room? The sampling speed. Thousands of steps.
Right. And that's win #2, and it's arguably even more impactful. The duality allows them to bring consistency distillation over to USDMs. They call their version Discrete Consistency Distillation, or DCD.
But hang on, didn't we just say discrete models lack that crucial property, the probability flow ODE, needed for consistency distillation?
Yes, the discrete model itself lacks it. But here's the genius move, enabled by the duality. The underlying continuous Gaussian process that the USDM emerges from does have a probability flow ODE.
Ah, so they use the ODE from the hidden continuous process.
Exactly. DCD uses the probability flow ODE of the underlying continuous process as a guide to train a distilled, discrete USDM model that can take massive jumps. It's like using the continuous shadows map to navigate the discrete world much faster.
That is really clever, using the theory to bridge that gap. So what kind of speed up are we talking about with DCD?
We are talking 2 orders of magnitude.
2, like 100 times faster.
Pretty much, yeah. They demonstrate reducing the number of steps needed and the number of function evaluations, or NFEs, from, say, 1024 for a good sample with the original model.
Down to
just 8 or 16. Really, really small numbers.
from over 1,000 steps to 8. That's transformative for practical use.
Absolutely. It suddenly makes diffusion models seem viable for applications needing much faster generation.
Does the quality hold up at 8 steps? That seems almost too good to be true.
They show results metrics and actual text examples suggesting the quality degradation is minimal. It's remarkably good, even with so few steps.
Okay, and how does this super fast duo using DCD compare to the other discrete models, like MDMs, when they are also sped up as much as possible, especially at these low step counts like 8 or 16?
That's where Duo really pulls ahead. In that low NFE regime, Duo significantly outperforms distilled MDMs.
Why? What makes the difference?
Gets back to that inherent property of USDMs, the self-correction.
Ah, right. The ability to revise.
Exactly. When you're forcing a model to generate in just, say, 8 steps, it's making huge leaps. An MDM might predict some words early on based on limited information, and then get stuck with them, even if they don't fit later parts of the sentence.
Leading to incoherent results at high speed.
Potentially, yeah. Duo, because its underlying USDM structure allows for that implicit refinement across the sequence, even during the fast distilled generation, tends to produce more coherent output, even when taking massive shortcuts. It handles the very few step generation much more gracefully. And they also had that interesting side note about the distillation process itself. They found using the direct weights of the teacher model worked better than using an EMA average, which is common. Another little optimization detail.
Okay, so let's tie it all together. The fundamental academic contribution is establishing the diffusion duality, this mathematical link.
Yes, formally showing how USDMs arise from Gaussian processes, defining the process on the discrete tokens, but leveraging the continuous insight. That's the core theoretical pillar.
And this theoretical pillar, the duality, directly enables the two major practical innovations.
Correct. Innovation 1, the Gaussian guided curriculum, leading to doubled training speed and improved model quality, making USDMs competitive.
And innovation 2, discrete consistency distillation, BCD, using the underlying continuous ODE to accelerate sampling by 2 orders of magnitude down to as few as 8 steps, where Duo outperforms other fast discrete models due to its self-correcting nature.
You got it. It's a beautiful example of theory directly enabling massive practical leaps.
So the bottom line for you, our listener, and for the field, what does this mean?
It means discrete diffusion models for language, specifically these duo-enhanced USDMs, are suddenly serious contenders. They're faster to train, they perform really well, sometimes beating autoregressive models, and crucially, they can generate text incredibly fast.
That speed really opens doors, doesn't it? For real-time applications, maybe interactive scenarios.
For sure. It lowers the barrier to using diffusion models where previously their slowness was prohibitive. And maybe more profoundly, the idea of the duality itself opens up new research questions.
Like, where else might these hidden connections exist?
Exactly. Could similar dualities exist between other types of discrete and continuous models? Can we port other techniques from the continuous world over? It suggests a whole new way of thinking about model relationships. So this deep dive into the diffusion duality, it really shows how digging into the fundamentals, finding these unexpected connections, can completely change the game in practical terms.
It's a reminder that there might be elegant links hidden beneath the surface of complex systems. Really makes you think.
So what strikes you the most from all this? The theoretical elegance of the duality itself, the practical impact of doubling training speed, or that mind-bending jump to 8-step generation?
It's honestly hard to pick. That generation speed is just staggering. Thanks so much for walking us through this paper and its implications.
My pleasure. It was fascinating stuff.
Until next time, keep diving deep.